Hey class, we're going to look at integration by parts as our next technique of integration. It's a very useful technique when you have an integral of two types of functions like algebraic and transcendentals. For example, you may have a combination of logarithm and trig, or some variation of those two. But this lineup gives you the formula at the very top. The integral of u dv is equal to u times v minus the integral of v du, which is just a whole lot of letters. And those I found in grad school an acronym LIATE, where each letter represents a type of function that you can see in your integrals. Where the hierarchy, if you go from top to bottom, whichever one of the two from your problem is higher on the list, that's the one that I normally assign to be U. And the one that shows up lower in the list is the one that I've assigned to the dv term. If you go back to the formula at the very top, those two components make up the original problem, the integral of u dv. So basically, when you look at your problem, you got to try to figure out which one you want to let be u, and then the other one's going to be dv. So let's hop into an example, and you'll see how this hierarchy works, what you assign u, what you assign as dv, and then these can be pretty long, so this will be a longer video than the first one. But I'm going to jump into an example, try to go slow. Of course, email me with questions as you have them. And so here we go. Okay, this first example, we have the integral of x times e to the 4x dx. X represents an algebraic term. E to the 4x represents an exponential. From the first slide, algebraic ranks higher than exponential. So we're going to let u be the algebraic term. And we're going to let the exponential be the dv. And again, it's all based on the ranking from top to bottom from your first slide. Whatever you assign to u, you're going to take the derivative of that. Whatever you assign as dv, you're going to take the antiderivative of. Because the power is 4x and has a derivative of 4, you got to be kind of careful when you take the antiderivative. Because there's no 4 in front of the e, we compensate with a 1/4. On the first slide across the very top, we had the integration by parts formula. So using these four items, we can now put u times v minus the integral of v du and that gives us our expansion. The integral in the back part we can simplify farther. I will pull that 1/4 out because it's a multiple or a constant, and we'll leave the e to the 4x behind before we take the antiderivative. Okay, just like we did at the very top right of your screen, this integral the e to the 4x, the derivative of the power is 4, but there's no 4 there. So think of it as if we put a 4 there, then we've got to take it back off, similar to this. Those two 1/4, when we get them together, are going to make a 1/16. And then we'll have the antiderivative and our constant of integration. Okay. That second integral, the e to the 4x, is pretty tricky. You might review the substitution technique from your first video, and that'll help get you through. But anyway, you can always check by taking the derivative of your answer, and it's got to give you your original problem back. Let's move into another example. Let's check out the integral of x times natural log x plus 3. In this problem, we have an algebraic times a logarithmic. Back in the first slide, logarithms rank highest of any of them. Algebraic ranks lower in the list. So we're going to let the natural log part be u. And we're going to let the algebraic part be dv. Taking the derivative of u, and remember, for natural log, your derivatives are 1 over the original times the derivative of the original. So that's 1 over x plus 3 times the derivative of x plus 3, which is actually just 1, dx. The antiderivative of dv is going to be x squared over 2. Now we're ready to use the integration by parts formula to start the expansion. uv since it's being multiplied, you can put it in any order, well, just whatever visually looks best for you. Okay, so that's u times v minus the integral of v du, those two parts. Be careful to keep your numerators and denominators lined up, but don't mix them up. There's just a lot of recopies, so these problems are pretty long to write out. Once you get your technique down, you'll be okay. Okay, I'm going to pull the 1/2 out. The fraction inside this integral, x squared over x plus 3, we can break that down using long division, and I'm going to write that across the bottom. I'm not going to actually do the integration until we get it rewritten. So let me change to a nice pretty blue ink. This fraction, if we break it down, which will give you flashbacks of college algebra, x into x squared x times x plus 3. Change your signs. X into negative 3x. Change your signs. And we get a remainder of 9. So what does that give us? Back in the integral, that's x minus 3 quotient plus remainder over divisor. I'm going to move to another slide. Okay, so that takes us to 1/2 x squared, natural log x plus 3, minus 1/2 integral x minus 3, plus 9 over x plus 3 dx. Basically just recopy the bottom of that slide right ahead. Okay, let's get down to it. We've got 1/2. Okay, I'm going to start some brackets here. In the integral, taking one term at a time, x has an antiderivative of x squared over 2. Negative 3 has an antiderivative of negative 3x. Nine over x plus 3. If we move the 9 ahead, move it to the front, then that opens up a natural log antiderivative. Because remember, derivative of a natural log is derivative over original, like a u prime over u. So we've got one more step to go. Let's start distributing the negative 1/2. Okay, now the denominator in this very last integral is x plus 3, which has a derivative of 1. That's the numerator. So this is a perfect example of natural log of the denominator plus c. Long problem, y'all. Our next example is going to be one that at first looks like it should be an integration by parts, but it's kind of sneaky. It actually doesn't require integration by parts. It goes back to our substitution technique from our first video. Level out that fraction bar. Okay, now natural log of x, I'm going to use that as a substitute with a single letter. Again, this is not integration by parts. This actually goes back to substitution. And let's see why. If I take the derivative of both sides, derivative of x is 1 over the original. That gives us a derivative of 1 over x dx. If we look at this problem carefully, our substitute in the numerator is just going to be u to the 4th. X dx, specifically 1 over x dx, matches up beautifully, and we can call that du, giving us a straightforward antiderivative. And then we put the original term back in, natural log of x, all to the 5th power, divided by 5, plus c.